I'm Eric Crable, a technical marketing engineer at Xilinx. Thank you for joining me on this quick sprint through one facet of the UltraScale+SEU solution. Xilinx provides a complete SEU solution for UltraScale+ FPGAs and UltraScale+ MPSoCs. The UltraScale+SEU advantage reduces total cost of ownership by providing reliability, availability, and serviceability. High reliability is achieved with ultra-low SEU rates through device architecture, circuit design, and process innovation. High availability is achieved with rapid error detection and mitigation responses, and high serviceability is provided through detailed event reporting and runtime event assessment. UltraScale+SEM IP is a key component of the UltraScale+SEU advantage. It intelligently manages error detection and mitigation of configuration RAM, driving high availability. It also generates event reports and event assessments for configuration RAM, serving the system detailed information about what is taking place, so the system can make informed decisions when exceptional conditions occur. In addition to runtime protection, it also provides error injection capability and diagnostic commands. These are crucial capabilities everyone should use for integration testing. If you're designing for reliability, don't you agree you should test the system response to exceptional conditions? The challenge with integration testing of this nature is creating realistic stimuli, and the UltraScale+SEM IP delivers. There are a number of ways to integrate the UltraScale+SEM IP into a system. Xilinx recommends using the monitor interface, which is a streaming, bidirectional exchange of ASCII characters. The monitor interface provides full observability and control of the UltraScale+SEM IP. The example design that comes with the UltraScale+SEM IP demonstrates connection to the monitor interface with a UART, but you can remove the UART and replace it with anything. For example, a mailbox or a register file, whatever you like for flow-controlled inter-process communication. Observing the UltraScale+SEM IP initialization via the monitor interface, you see it announce itself and indication of what features are enabled. Then you see it pass through 3 checkpoints while starting up the hardware scanning, reaching the observation state in which runtime protection is active. Normally you'd leave runtime protection active, but you can change from the observation state to the idle state to request a status report or use the error injection and diagnostic commands. This shows the UltraScale+SEM IP receiving a command to go to the idle state, followed by a command to request a status report. Among other things, the status report indicates the maximum frame number, which is how many configuration RAM frames exist in the device. With UltraScale+SEM IP in the idle state, you can send commands for error injection. An error injection command specifies a single configuration RAM bit address, and the best approach is to use linear frame addresses which range from 0 up to the maximum frame number. Most configuration RAM locations are physically implemented, but it's always a good idea to use the diagnostic commands together with the error injection command so you can see the before and after. You can build up multi-bit errors through multiple error injections. In some devices, including the KU9P we're using today, you may notice ranges of linear frame addresses which do not respond to error injections. In the implemented device view, you can visualize these as areas of the die that do not contain programmable logic. In all devices, at the very end of the linear frame address range, you will also encounter a few frames with configuration RAM locations that are physically unimplemented. So, where in frame should we inject errors? You can do it anywhere. In the UltraScale architecture, the center word of a frame holds part of the frame-level ECC checksum, so introducing errors here is a safe place because these bits do not control a programmable logic resource. In other words, there's no risk of hitting your design. I'm going to use linear frame address 8000 hex. The first command shown here is query to look at the data in the configuration RAM at this linear frame address before the error injection. In UltraScale+ devices, a frame is 93 32-bit words, so the query command returns 93 lines of 32-bit words, each word shown as an 8-digit hex value. The output on the slide is abridged, except for the center word, which here is shown to be 0, but it could have any value based on the bit stream resident in the device. The next command is an error injection command. You give it a 7-digit linear frame address and a 3-digit offset in the frame. The offset 5C0 is in bit 0 of word 2E, the LSB of the center word in the frame. The last command shown here is query to look at the data after the error injection. The output is abridged again, except for the center word. I'm interested in seeing if I successfully changed its LSB. This shows the UltraScale+SEM IP receiving a command to go to the observation state, which enables the configuration RAM scanning. Once in observation state, the injected error is detected, and the detection report provides the detection timestamp, physical frame address, and linear frame address. What follows is the correction report, showing a correction was made in bit 0 of word 2E, the LSB of the center word in the frame, where the error was injected. If the optional error classification feature is enabled, a classification report is also generated. If the error is correctable, UltraScale+SEM IP returns to the observation state and continues scanning, otherwise it changes to the idle state. Let's exercise some basic integration tests with the UltraScale+SEM IP example design in the KU9P on the KCU114 board. The UltraScale+SEM IP settings are all defaults, except I changed the clock period. The KCU114 has a 74.25 MHz oscillator, so I changed the clock period to 13,468 picoseconds when generating the IP. Then, after opening the example design, I changed the clock input from single-ended to differential and updated the XDC to match the pin locations and signaling standards for the KCU114. I generated the bitstream in advance so we could jump right into using it. You can see the download is completed and the UltraScale+SEM IP has already transmitted an initialization report. Now we can try a few tests. Test 1 is going to be a correctable single-bit error. Most SEU are single-bit. So go idle, give me a status report. I was curious what the maximum frame is. I see BBB6 hex. Let's look at a frame. It's pretty much all 0. Let's scroll up and just confirm it is 0 everywhere. Yes. Let's inject an error in the center word. Let's check if it worked. It did. Right here. Okay, so now let's turn it loose. You can see it detected and corrected the error. This is just like what I showed earlier. Let's try test 2, a correctable 2-bit error, intraframe. Some SEU are small multi-bit, but not many-bit. I'm going to do this without the queries now. Idle, inject at this address, and inject at that address. Go back to observation. Okay, wow, it found it and it fixed it. You can see here in the correction report, it identified both of the bits that had the errors injected in them as being corrected. Now let's try test 3, a correctable 2-bit error in a single frame. Again, some SEU are small multi-bit errors, but not involving many bits. So again, I'll do this without the queries. Go to idle, inject. Oh, I made a mistake. Okay, fabulous. What I see here is at linear address 8000, it corrected this bit, and at linear address 8001, it corrected this bit. So that test also succeeded. What we just covered here represents about 99.9% of the SEU you'll ever encounter in UltraScale+ devices. The point of integration testing is not to relentlessly pound on the system, but to answer a critical question. Is the system responding as designed to the event reports? Answering this question is easy with the error injection capability of the UltraScale+SEM IP. Now you've seen UltraScale+SEU solution integration test is easy. I hope that what we just finished makes you want to try it. This how-to was for the KCU114, but the design porting and commands apply to any board with a UART and an UltraScale+ FPGA. Thanks for spending your time with me.